Okay, welcome everybody. This is week 9 webinar for the online stats class. And let me tell you the plan. This is all going to be all about the chi-square distribution. So as always, I'll answer any questions you might have. And then after that, I'll just kind of explain a little bit, just the basics of what the chi-square distribution is, just show you a picture basically. And then we'll see using it for doing hypothesis testing. So we're going to be using it for hypothesis testing on something that we haven't really dealt with before, and that is dealing with qualitative survey questions that are not just yes, no. So someone was asking about what my shirt says. Now you can see it, I think. It's kind of a joke. It's a math joke. And so we're going to be looking at the chi-squared goodness of fit test. We're going to look at the chi-squared test for independence. And we're going to look at the chi-squared test for homogeneity. So again, that'll mean nothing to you right now, but by the end of the lecture, it'll hopefully you'll understand what it's all about. And again, it's going to allow us to do hypothesis tests on surveys where you don't have a yes, no, or a quantitative survey question. Things like what is your favorite color, that kind of stuff, and others too. So that is the plan. This is week 9. Week 9 is an odd week, so no exam this week. You get that little break. But that what that means is that you have a little extra time this week. So I strongly, strongly recommend getting a lot of progress on your project because this week you have a little less to do for regular stuff. So it's a good week to get progress on your project done. That makes sense. And I'll be watching the Project 2 discussion board. I strongly recommend this week to write down what your idea is. And, also, it's always a good idea. And this is why I have it on the discussion board instead of just you emailing me. That way you can see kind of feedback and what works and what doesn't work from your classmates. And you get to see that idea because some things work, some things don't work. So one already happened in I think the sample size, I don't think you could get a large enough sample size. The population be too small. So don't forget the population needs to be large too. Okay. And not 31, but the population should be very large. So that's just a note. Um, so are there any questions? Are there any questions about anything from the class? This is a good time to ask. Always happy to answer questions. Okay, if you don't have any questions, let's have a question for you. See if you can put in the chat box. What? See if you could post a distribution that we've already covered in this class. And post one that someone else didn't post. So put in the chat box a distribution that we have covered. We've covered a bunch. So see if you can type in. If you type in fast, you can be the first one, and then you'll get the one that you remember. Okay, got one that said uniform. What else? There are a bunch. There's some others. Yeah, the normal distribution. Okay. And so those were the binomial distribution. Good. So we've had the uniform, the normal, we've had the binomial, and now we're going to have what's called the chi-squared distribution. So let me show you kind of a picture of what it is. And it turns out, by the way, the other one that we've had that's really important is the student's t distribution. That was, remember, kind of like it's a modification of the normal distribution to the fact that you don't know the population standard deviation. So that was kind of how that worked. Okay, and the student's t distribution turned out to have something called degrees of freedom. If you have a larger sample size, it changes the distribution shape. The same thing is going to be true for the chi-square distribution. I want to let you know right here this symbol, this is not an X, by the way. This is actually a Greek letter, and it's the Greek letter chi, C-H-I, is how we usually read it. And squared, I won't get into the math of it, but one thing about when you square something, don't get negative numbers, so there won't be a left-hand side. So let's take a look at the chi-square distribution. And there's something called degrees of freedom. And for example, if the degrees of freedom is 4, then it looks like this. It's kind of a distribution. It's unimodal. It is skewed to the right, always positive. There's no negative numbers, no negative values that could ever happen. Okay. On the other hand, if we go to, say, 1 degree of freedom, then it's very skewed to the right. But if we go to a whole lot of degrees of freedom, like 20 degrees of freedom, what does it kind of look like? Not perfect, but what does it kind of look like? Yeah. Yeah, it kind of looks like a normal distribution. If you have a whole lot of degrees of freedom, it's more bell-shaped, and that's what it looks like. But it does stop at 0, unlike normal distributions. They don't stop at 0. So that is the chi-square distribution. We're not going to do much math with it because we don't do much math in this class, but we're going to be using it pretty much for everything in this entire chapter. Okay, and in case you don't remember, this is chapter 11, which is what we're looking at. I do want to give you another heads up. Don't even think about using it for your project. Okay, project 2 is really about chapter 10. So don't even imagine going into anything in chapter 11 or chapter 12 or chapter 13. Stick with chapter 10. Does that make sense? Okay, so that's the picture. So now we're going to use it. Okay, and the chi-square distribution is used a whole lot in research. It's one of those things that when you read journal articles, and in this week's discussion post, for example, that you have to do a journal article that is peer reviewed. So it's not that hard to find kind of things that use the chi-square distribution because it really is one of the top distributions that's used in research. So I can tell you that, but until get into, upper division classes, you may not see it that much. So here's an example. And that is in California, 40% of all California residents are Latino. Okay. 34% are white. 16% are Asian or Pacific Islander. And 10% are other races. Okay, and that could be African American, it could be Native American, or whatever it might be. So one of the things that we might want to, be interested in is the distribution of race is different for California community college students. Because one of the things about, our goal at the community colleges is to represent our students and represent our population. Okay, so we want to do our best so that we have good diversity and, we accept pretty much anyone who wants to come and not like this race or that race. We want everyone to be able to be happy coming here. And we hope that we'll have, similar to what California looks like. Okay. So I should say, suppose a survey was done because I really didn't do a survey, but you can imagine a survey done of 300 California community college students, and 125 were Latino, 42 were white, 33 were Asian or Pacific Islander, and 50 were other races. What can be concluded at the 5% level of significance? Any questions at all on this example? Okay, think about the survey question. If you think about the survey question and think about the answer to the survey question, what would an answer to the survey question be? Give some examples. Maybe if someone asked you the survey question, what would you say? You can pop in the chat box. Remember, the chat box does not go public. So what would your answer to the survey question be? If you were one of the 300 community college students they asked, how would you answer it? So put in the chat box. This isn't supposed to be hard. Okay, I'm not seeing anything. So let me remind you, the survey question itself would be, if you think about it, what is your race? Right? Because that's what we're interested in. So can you answer the question in the chat box? This isn't supposed to be hard. Okay. So pop in the chat box what the answer is. Okay. So what you can notice, and we don't have a lot of answers, but you didn't say yes, you didn't say no, you didn't say 33. Yeah, you gave a word. Does that make sense? And we have not handled anything like this before in terms of doing a hypothesis test. Is that clear? So none of the hypothesis tests that we have done yet in this class will work. Is that clear? Because there's not a yes no question. There's no numbers as an answer. It's just words. Any questions on that? Okay, so here's what we're going to do. We're going to use a chi-squared test. And we need an H naught and H1. And I want to give a big heads up. Okay. Do you have to come up with a code? I'm not sure what you mean by a code. So I don't know what you mean by that. Okay, never mind. I won't mind. Okay, so in particular, we're going to do an H naught and H1. And I want to give you a heads up, and that is, if you remember, if it is something from chapters 9 or 10, you must use symbols and not words to write down H naught and H1. And I did grade the discussion post assignments and your exam. And a lot of you didn't use symbols, even though I like screamed, you got to use symbols. Okay. On the other hand, for chapter 11, you don't use, we don't have to use symbols. In fact, you shouldn't use symbols. It's really hard to do that because you don't even know what symbols to use. Okay. You can use words. Okay. So you're saying it was hard because of the drop-down menus, but you can use your symbol for mu could be MU, and that's okay. And then you can do the little subscript button, and then you can do, the first letter. And then you have the equal sign. Does that make sense? Or the greater than sign or the less than sign. That's easy because that's on the keyboard. Does that make sense? So even if you can't find the drop-down member, that can work. Okay. Okay. On the other hand, so if you want subscripts, you just do the shift next to 0. Okay. You just do that next to 0 thing, and that means subscript. Okay. So on the other hand, for chapter 11, we're going to use words. So here's what we have. H naught is, I'll be happy. That's the kind of thing you can come to my student hours. You can also ask me after the webinar how to do things, and I can show you that kind of stuff. Does that make sense? Always happy to help you out, but that's more an after, not during the webinar. Okay, so H naught. You do have to write H naught with a colon. Okay, that's always true. And then you write, in this case, the distribution of races at California community colleges is the same as the distribution of races in California. And you might notice, let me say it again, but differently, the distribution of races at California community colleges is the same as the distribution of races in California. Why did I scream and yell that word? You should be used to it now. It's not my first time. And that's H naught. Yeah, it's important and not just important, it's required. You don't use that word in your H naught and H1, it turns out. When you're doing this kind of hypothesis test, you're going to lose a lot of points. Okay? So it's one way for me to make sure that you're actually watching the webinar and not just using AI, for example, because AI won't do this. Okay? Whereas H1, the nice thing is you can copy and paste H naught and then add in the word not. H1 is the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions? Any questions on this? So notice that this is all about the distribution. It's not a proportion. It's not a mean. It's a distribution. Okay, so what we're going to need to do now is we're going to use what's called the goodness of fit test, often called the chi-squared goodness of fit test. So that's what it's called. And what you need to do is you need to create a table. So for the table, what you're going to do is you're going to have rows and columns. And by the way, on the calculator, for example, if I remember right, it's the opposite because it fits better on the page, but for this has to do with how it fits, is that what we've got here is the columns are all the possible answers someone can give. And the rows are going to be O. O stands for observed, and E stands for expected. So observed is very simple because if you look at the question, 125 were Latino. So under Latino, observed, I put 125. It says 92 were white. So under white, observed, I put 92. We had 33 Asian or Pacific Islanders. So under Asian Pacific Islanders, I put 33. And then we had 50 other races. So under other, I put 50. Any questions so far on creating the table, especially with the observed? Any questions? Okay, so the next thing you do is we need to come up with the expected, E for expected. And what that really means is that if H naught is true, how many would you expect to have of each race? So the survey had a sample size of 300. So if H naught is true, then 40% of them should be Latino, right? So to get the expected number of Latinos, we take 40% of 300. And 4 times 3 is 12. 40% of 300 will be 120. You can multiply it in a calculator, whatever it takes, but you need to be able to get that expected. Any questions on how I calculated the expected? I took 0.4 times 300 and I got 120. Okay. We would expect 34% of them to be white. Well, what is 34% of 300? That's 0.34 times 300. And that is 106. Sorry, 102. I did my head wrong. Okay. And then we expect 16% to be Asian or Pacific Islanders. And 16% of 300 is 48. And then we would expect 10% to be other races. 10% of 300 is 30. Any questions on that? Any questions on how I came up with the table? Okay, a little bit of math, but the math is just multiplying the percent times the sample size for each of the percents. So nothing too intense. Okay, so you're used to this. We've got our H naught, we've got our H1, we have our kind of like data kind of stuff. Any guess on what the next step is? We've decided to use a goodness of fit test. What's the next step? Again, we've been doing this for a long time now. Yeah, we use a calculator. So I'm going to go to the calculator. And what calculator number should we use? This should be really obvious. Yeah, it's 21. Notice we're getting towards the end. We're almost done. So I can click calculator 21. And what it says, type in the values for the observed and expected sets separately by commas. For example, 2 comma 4 comma 5, etc. Then hit calculate and the test statistic chi-squared and the p-value p will be shown. So it first asks for the observed. And for the observed, we had 125.92. So 125, comma, 92, comma, 33.50. So 33, comma, 50. And for the expected, we had 120, 102, 120, comma, 102, comma. And then we had 48 and 30. 48, comma, 30. Any questions? All right, and I hit calculate. And it gives us our test statistic, chi-squared, is about 19.2. And it gives a p-value of 0.000247-ish. Okay, it also shows some pictures. So this is the shape of the chi-square distribution. And that's what we've got. Okay. So now what we're going to do is write down what chi-squared and p are, 19.2. I'll leave it as. And our p-value was 0.000247. Any questions on that? All right. Well, at this point in the class, you should know how to look at this p-value and come up with a conclusion. So what do we do? Again, we've been doing this for weeks now. What can we do? Okay, interpret p. Now we're going to use the p. So 0.000247. Okay, is that a large value or a small value? Yeah, it's small. Okay, so usually when you're talking about this chi-squared, usually the level of significance is not given, but we know how to use the numbers now. So this is it's not just a little small, this is very small. It's less than 0.01. So now we can write down the conclusion. And when you have a very small, so less than 0.01, you can say there is strong statistically significant evidence to conclude. Okay, this is not new. We've been doing this for a while now. Any questions on that so far? Or to conclude that? And the good news is we have already written down H1. The distribution of races at California community colleges is not the same as the distribution of races in California. So I just copy and paste the distribution of races in California community colleges is not the same as the distribution of races in California. And there's my conclusion. Any questions? Any questions at all on the conclusion? All right. So one of the things that you might ask is, well, if the distribution's not the same, how is it not the same? Is it that we have, too many whites, too many Hispanics, too many Asians, too many Latinos, too many others? Um, and I'm going to give you the news on this, and that is we will not find out how to do that in our class. Any guess on what you'll have to do to find out how to do that? To see which is the one that's, kind of off the chart on the high side or low side. Have to ask everyone? No, no. Something it may be more painful. Okay, you'd have to take a statistics class at a university that's upper division. Okay, so there are hypothesis tests to do that, to go to the next level and say, okay, what's the one that's so, that's so off? Which is the race? Which is making it not fit? Do you see that? And I'm going to let you know, since we're getting towards the end of the class, we cannot do every single type of statistics test, hypothesis test in our class because we only have so much time. Okay, and this is a lower division class. So I will let you know there are a lot more hypothesis test types than what we do in our class, but we can only do so much. I usually don't get students complaining that there's not enough information in our class and it's just too slow. That's not usually a complaint we get. So, but I will tell you, if you want to get a master's degree, for example, you may have to learn this stuff. Okay. But not for, definitely not for just a transfer class. Any questions at all on this example? Okay, so let's do another example. Let's look at it. So notice this was a goodness of fit test. And just note a goodness of fit test is when you have a known distribution. We knew that the distribution of all of California, right? That's a population distribution. We know the population distribution of California is 40%, 34%, 16%, and 10%. But we have this unknown distribution, and we want to see if the unknown is the same as the known. Does that make sense? And that's what goodness of fit test is all about. Okay, now we're going to look at a different type. So let's do another example. Okay, so the example is, does it matter what season a person was born when it comes to the type of car they drive? Okay, table below shows the season and car type of a survey that was done. So you'll see now we have, the 73 means that of the survey that was done, 73 of the people were born in the spring and drive a sedan. Okay, for example, 62 people that were surveyed were born in the winter and drive an SUV. So that's how you read these numbers. So the question is if you happen to know what season a person was born in, then are they more, can you kind of get a better guess on what kind of car they drive? Okay. Do you think that might be true? Or do you think that's, has nothing to do with the kind of car people drive? For example, I was born in the summer. Okay. I was born in the summer and I don't drive much, but when I do drive, I drive an SUV. Okay. That's just me. Okay. So what do you think? So that's actually really important to kind of see that. Okay. So if you think about, for example, in business, you would say, hey, if you happen to know when someone was born, we know what kind of, let's say you're selling cars. We know what kind of car to show them because they're more likely like this kind of car. Do you see? Or in biology, instead of this example, you could have maybe, for example, what blood type they have and what is the most likely cause of death. Okay. Do you think knowing someone's blood type will help you out in deciding how they might die? Okay. And again, people in the medical profession really need to, if that is the case, then it helps to know those kind of things because if blood type matters like that, then if somebody is tested for, say, O positive, then, and you find out that O positive people might be more, likely to have cancer, then you might want to make sure that they get tested for cancer more often. Do you see that? Okay. By the way, I have no idea if that's true or not in terms of, if that, if it has anything to do with it, but it might. Okay. And I know that DNA does, for example, that's a much longer list of things that could happen. Any questions on how this works? All right. So this is different. This is not the same thing. This is not about distributions, right? It's not this distribution versus this other distribution, a known distribution, an unknown distribution. What this is knowing one thing, will that help you understand the other? And we actually have talked about this, but it was a long time ago. Okay. And that was when in chapter 3, we talked about independence and dependent data. So what we're going to be doing is we're going to do what's called a chi-squared test for independence. So we have a new test name. And by the way, on the exam and on your discussion post, you are going to be asked to identify the test that you're using. So we had good as a fit, and now we have a chi-squared test for independence. So make sure that you can, write down those words. Does that make sense? And it's used when we have two survey questions that are both qualitative, and we want to see if they're independent or dependent. Okay, so notice the survey question. The first survey question would be, what season were you born in? Okay, and I was born in the summer. What season were you born in? You can pop in the chat box. I hope you all know your own birth. Okay. So we got someone who might be their birthday today. June. Okay, so notice what you're saying is words. You're not saying 74. You're not saying no. Okay, it's words. This is qualitative data that's not a yes no question. Okay. All right. And then the second is what kind of car do you tend to drive? So I drive typically an SUV. What kind of car do you tend to drive? Sedan, SUV, or other? So what kind of car do you drive? Okay. So you'll notice that what you're answering are words, right? Sedan, other. Do you see that? Not a number. You're not giving me a number, you're given words. So this is two survey questions where both are qualitative. And we want to find out if they're independent. Okay, if they're independent, the knowledge of the first survey question, what they answered, tells you nothing about the second. If they're dependent, then if you know their answer to the first question, then that will help you kind of, figure out, you have a higher chance of something else in the second. Does that make sense? Any questions on what the test for independence is all about? All right. So just like we've done in every other example we've had in the last, few weeks, the first thing you do is think about what your, ideas are, and then what you're going to do is after you write down the type of test you're going to use, you're going to write down H naught and H1. And remember, today we're going to be doing for chapter 11 only. It's all in words, not in symbols. So here is what H naught and H1 look like. H naught is the season a person was born in, and the person's card type are independent. Notice I screened that word. And H1 is the season a person was born in, and the person's card type are dependent. And I screamed that word. Hopefully, you all know why I screamed it. Why did I scream it? Yeah, you must use that word in H naught and H1. You must use the word independent in H naught, and you must use the word dependent in H1, or you're going to lose points. Okay? So, what I've noticed is I think a lot of people don't pay attention to the webinar. Okay, hopefully, all of you are paying attention and writing this down. Okay, because I've noticed that it doesn't, a lot of people just ignore what I say, but this is a requirement. Got it? Okay, so you're used to this. Once we have H naught and H1, we have our data here. What's the next step? You're really used to this, I hope. Yeah, we calculate. We go to the calculator. Okay. By the way, this is not a goodness of fit, so this calculator won't work. So I can go back to the calculator menu. I tried to make the calculator really easy to read if you understand what we're doing. So what calculator number should we be doing? Yeah, it's 22. Not only did I make it easy to read, but I also put it, hopefully you noticed, in order in which we do things. So it's going to be a test for independence. Any questions on that? So I click on test for independence. And what it says is enter in the observed values and hit calculate. And the chi-square test statistic and the p-value will be calculated for you. Leave blank the last rows and columns that don't have data values. Okay, so now we just put in the values. So the first row is 73, 81, 76. So 73, 81, 76, and 78. The next row, 65, 68. So 65, 68, 62, and 64. The third row, 43, 51. 43, 51, and then 48 and 50. Any questions at all on this? All right, and I leave everything else blank, it says. And then I just hit calculate. And there we have it. Okay, we have our chi-squared, which is about 0.48. That's our test statistic. And we have a p-value, which is about 0.998. Really high. So 0.48. And our p-value is 0.998. Any questions? Any questions on doing this calculation? Okay, so as you're used to, once you have this, then we have to write our conclusion. Okay, so if you have a p-value of 0.998, what does that tell you? If p is 0.998, I'm hoping you all know. This isn't any new thing. We've been doing it for weeks now. Looking at the p-value. Let's see, I'll put it in the chat box. Hopefully you're listening. Okay. All right. If you don't remember, then p is very large. It's bigger than any level of significance you would ever use. So if p is 0.998, you fail to reject the null hypothesis. And the conclusion, remember, the first word is there. That helps out. There is statistically insignificant evidence to make a conclusion that. And then what you can do is you just copy and paste H1, the season a person was born in, and the person's card type are dependent. Okay? And remember, this big IN is really important, insignificant. So that means it's a very fancy way of saying we did the study and we know nothing. Okay. By the way, do you think the issue might be that our sample size wasn't large enough? Do you think a bigger sample size would be a good idea here? What do you think? Okay, so the answer is no. This is a gigantic p-value. Okay, it's not a guarantee, but when you have such a big p-value, it's time to give up. It usually means that H naught was just probably true. You can't say for sure it was true, but you give up. If the p-value is say 0.13, then you might want a bigger sample size because then you're kind of close. Do you see? But 0.998, that's too big a p-value. And I do want to give you a honesty. I made up these numbers, but you can imagine doing this survey, right? I hope you can all imagine it. Okay, so it's very important in your project, for example, to understand what the p-value tells you. Very, very important. And I talked about that a couple weeks ago when we went over the p-value. Okay. In this chapter, I don't ask you to interpret the p-value. It's a little complicated. I also, so in this chapter, it's basically you're just doing the hypothesis test and stating the conclusion. Okay. I do want to give you one more thing that won't affect you at all in this class, but it might affect you after this class. And that is, if you look at the calculator, there's only 5 columns and there's only 10 rows. If you have more than that, more different types, so let's say you wanted to look at, I don't know, how about the color of someone's hair versus what state they live in America, then, how many states are there in the United States? Yeah, there's 52 states, so this wouldn't fit. So I want to give you a heads up for this calculator only works for, not giant groups, but you'll never have anything bigger in this class. Does that make sense? But maybe in your future someday you'll do a study and then don't use this calculator. You can use the spreadsheet program I did actually can handle it, but it can't handle this one. Another thing is it turns out if you switch the rows and columns, you get exactly the same answer. It's one of those interesting things about the chi-square test for independence. It doesn't matter which side you're on. So if we did 73, 81, 76, 78 as the first column, and then 65, 68, 62, 64 as the second column, and 43, 51, 48, and 50 as the third column, and hit calculate, you'll get exactly the same chi-squared and p-value. And all I can tell you is trust me. If you really want to know why, you need to become a math major because the math is pretty intense. So hopefully you all trust me. Okay, so any questions at all on that? Okay, ready for another one? Okay, so here's another example. Okay, oh, I didn't think I wrote this down. There is statistically insignificant evidence, because our p-value is so big, to make a conclusion that the season a person was born in and the person's car type are dependent. I kind of wrote it, but I didn't like yell it out. So that's the conclusion. So notice the word insignificant because our p-value is too big. All right, so the next question is, do single men and women take the same type of vacation? What do you think? Okay, so the table below shows the results of the study. And we have male and female. We have international, out of state, and more local. And I made these numbers up, so imagine that there was a survey done. Okay. So, it doesn't mean they go together, but just, it's the same type. If you know someone is a man, or does that give you a better idea of where the next vacation might be? If you know someone is a woman, does that give you a different idea of where their next vacation might be? Or maybe it has nothing to do with whether you're a man or woman, just people are people. Okay? Does that make sense? Okay, and I did make up this data, so don't like, tell all your friends that, yeah, I read this, I heard this statistical analysis. I made this up, but it could be done. Okay. And again, we have 29 of the men surveyed are going to be taking an international vacation the next time they travel. 27 are going to go out of state. 33 are going to be more local. For the female, 38 were international, 42 were out of state, and 36 were more local. Any questions at all on what the question is? Okay, this is not a test, a goodness of fit test, because there isn't a distribution we know. Okay, it's not asking whether they're independent or dependent. It's whether the distribution for men is the same as the distribution for women, and we don't know either of them. Is that clear? So this is actually a different type of hypothesis test. And the type of hypothesis test we're going to use, actually, let's do it this way, is the chi-squared test for homogeneity. Anyone know what that word homogeneity means? It's not a math word, it's an English word. But it's a, kind of a fancy English word. You've all probably heard homogenized milk, right? Same, it's the same thing, homogeneity. So, have you heard the word homogeneity? Yeah, it's kind of like mixed, okay, equal parts. So, it's kind of testing to see if male and female are basically equal, or are they different from each other? Do you see that? That's kind of the idea. So that's why it's called the chi-squared test for homogeneity. If you don't like that, don't get mad at me. I didn't name it. But that's why it was named. All right, so the next thing we have to do once we have decided what kind of test we're going to do is we're going to have to write down the null and alternative hypotheses. So here we go. H naught is the distributions. Notice this S because we have the distribution of men and we have the distribution of women. So the men's travel type and the women's travel type. So the distributions of vacation type are the same for men and women. And H1 is the distributions of vacation type are not the same for men and women. Notice I said the word distributions very loud because that's required if you're going to be doing a test for homogeneity. You have to have that word in there, okay, in our class. So make sure you do. Write some notes so that you make sure that happens or you lose points. Okay. Any questions on these the H naught or the null hypothesis and the alternative hypothesis? The distributions of vacation type are the same for men and women. The distributions of vacation type are not the same for men and women. Notice this is not about independent or dependent. This is not a goodness fit test because we don't know any specific distribution. This is comparing two distributions where we don't know either of them. So what's the next step? You better all know this. What's our next step? Yeah, we go to our calculator. And as I mentioned, this is not a test for independence. So I go back to the calculator menu. And I hope you can all tell me what calculator to use. Should be obvious. Yeah, this is a test for homogeneity, calculator 23. Any questions on that? Okay, so it is required that you know the names of the test. Okay, one is I could ask you, I will ask you what is the name of the test to use. And the other is if you don't know the name of the test, you won't know which calculator to use. This is a test for homogeneity. Okay, and what it says is enter in the observed values for each of the two samples, A and B, and hit calculate. And the chi-squared test statistic and the p-value will be calculated for you. Leave blank the last rows that don't have data values. Okay, and now we just plug them in. So we have 29, 47, and 33. So 29, 47, 33. And for B, we have 38, 42, 36. 38, 42, 36. Any questions on putting it into the calculator? Again, my goal when I made this calculator is to make it as easy as possible. Okay. I do want to give you another heads up. If there were, instead of 3 different types of vacation places, if there were 11, you can't use this calculator because this only has 10. So then you have to use a different calculator, spreadsheet or something like that. And hit calculate. Okay, there we go. Chi-squared 1.4038699. P is 0.4956. Okay. So here's our picture, our chi-squared. And so 1.40 about for chi-squared. So 1.40. And the p-value was 0.4956. 4956. 0.4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. 4956. So 0.4956. Okay, if you have a p-value of 0.4956, hopefully you know the conclusion, which is, how does it start? Give me the first few words, put it in the chat box. Because a lot of people have trouble with this on the exam. But it's very important that you know the first few words to put in, and I require that you use those words when you have a p-value of 0.4956. In in chapters 9, 10, and 11, so the first few words are kind of always the same when you have a big p-value. What is it? Remember? Very important to know these words. This is not new. Last week, the week before. Yeah, there is almost, except that p-value is large. So it's not there's statistically significant evidence. It's there's statistically insignificant evidence. Does that make sense? Because our p-value is too big. So we can say there is statistically insignificant evidence to conclude that the distributions of vacation type are not the same for men and women. So insignificant means that we can't make that conclusion. Is that clear? Okay, so the hope is if you understood chapter 9 and 10, this isn't too bad. Any questions at all on this chi-squared test for homogeneity example? Okay. By the way, what do you think the hardest part is going to be in this chapter? And by the way, my definition of hard is students have trouble with it. Any guess? Yeah, when P is large, then it's statistically insignificant evidence. If P is small, there is statistically significant evidence. That was how hypothesis test works. Okay. Any guess on what the hardest part where people have trouble with in this chapter? Yeah, which test to use. Exactly. That's going to be tough because you got to understand. So let me go through again. If you have a known distribution and then you do a qualitative survey question to see if that is the same as your known distribution, that's goodness of fit. If you have two survey questions and you want to find out if they're independent or dependent, that's a test for independence. Okay. And then if you have two survey questions and you want to find out well, one of the survey questions just breaks it up into two groups, and you want to find out if the distribution for the first group is the same as the distribution for the second group of the second question, then that would be test for homogeneity. Any questions on that? Okay, let's do one more example, which isn't too long. We're probably going to finish a little early today because today's one of the easier weeks. Okay, so now let's look at this. A study was done asking 100 people how many minutes they spent in the shower last time they took a shower. The mean was found to be 16 minutes and the standard deviation was 4 minutes. The table shows the results. Is the distribution normal? So remember that when we looked at the central limit theorem, if you know the distribution is normal, then we know the sampling distribution is normal. So sometimes you want to find out, is the distribution normal? And this is going to be a way to do it. Okay. This is one way. It turns out there's a way that's more detailed, harder, but shows it even better. And that is something that you do not in this class, that would be an upper division statistics class, a different test. But you could do it with what we've got. So here we had 20 that were less than 12. We had 73 that were between 12 and 20. And we had 7 that were greater than 20. Okay, 20 minutes spent in the shower. Last time they took a shower. Okay, does that make sense? All right. So what I'm going to do now is I'm going to find the observed and I'm going to find the expected. Okay, and this is going to be a chi-squared goodness of fit test because the distribution that we know is the normal distribution. We want to see if the distribution of shower time fits the normal distribution. Does that make sense? And the observed was 20, 73, 7. How do we get the expected? Here's a hint. What's important about the numbers 12 and 20 for this example? Does anyone see it? Low, high, but what's specific about those words? In other words, had it been 13 and 24, that would have been actually much harder. Anyone see it? Okay, so the key is the mean is 16. The standard deviation is 4. So 12 is 1 standard deviation below the mean. And 20 is 1 standard deviation above the mean. Does that make sense? So this is kind of the nice way of deciding if you have a normal distribution. Any questions on that? So now we got to remember what percent or what proportion of the data, if it is a normal distribution, should lie within 1 standard deviation of the mean. Does anyone remember that number? The hint is it's called the empirical rule. Do you remember what percent lies within 1 standard deviation of the mean? It's been a long time, but we did it. Chapter 2, and we also did it in chapter 6. And remember the percent? No, it wasn't 96. Good try, though. Okay. It was 68%. There we go, 68. Yep, someone got it, just as I was saying it. Okay, so 68% is what we would expect to be between 12 and 20. So what we can do is we can take 68% of our sample size. I made the sample size nice, so I can do this in my head. If you had 100%, hopefully you all know what's 68% of 100. This is really obvious. Yeah, 68. So our expected would be 68. We would expect to have 68 people of those 100 having taken their last shower spent between 12 and 20 minutes. All right. So the good news is 12 and 20 are 1 standard deviation away. So everything is symmetric. If there's 68% inside, then there's 32% outside. So how much is left and how much is right if there's 32% total outside? Not too hard a question. If there's 32% outside and it's symmetric, what percent will be to the left? It's not 18, yeah, 16, because 32 divided by 2 is 16. So 16, and 16% of 100 is 16, will be both of these, 16. Any questions on that? Okay, we're using a goodness of fit test because we have our known distribution, that's called the normal distribution. And we have our unknown, and that is the distribution of taking a shower time to take a shower. So now we write H naught and H1, and remember, you have to have the word distribution. So H naught is the distribution of shower time is normal. And H1 is the distribution of shower time is not normal. Any questions at all on what we've done so far? So what's the next step? Yeah, we go to our calculator and tell me which calculator to use. What calculator number should I use? This should be easy. Yeah, it's 21 because we're doing a goodness fit test. So go to 21. Okay, and we want to enter the observed separated by commas and the expected separated by commas. So the observed were 20, 73, and 7. 20, comma, 73, comma, 7. And the expected were 16, 68, and 16. 16, comma, 68, comma, 16. And I hit calculate. And there we go. It gives us the chi-square distribution, the chi-squared value. So the test statistic is about 6.43. Let's write that down. And our p-value was about 0.04. Any questions on finding the test statistic and the p-value? Okay. By the way, just want everyone to know, you do need to use our calculator. Okay. It rounds better. It does it right. Often I notice that you're doing a lot of stuff by hand and you don't get a good answer. Use this calculator. Okay. I tried to make it really easy to use, but you need to use it. If you use AI, it's going to be really bad for you because it doesn't use this calculator and it does rounding bad things. It does rounding mistakes. So don't even think about using AI. Okay, use this calculator. Got it? All right, so then we need to state our conclusion. And by the way, if the p-value is 0.04, what does that tell you? So p-value is 0.04, what does that tell us? Yeah, reject the null hypothesis. There is statistically significant evidence, but note we cannot say there is strong statistically significant evidence because 0.04 is not less than 0.01. We just say statistically significant evidence. So we have the evidence, but it's not strong. Do you see how it works? So we can say there is statistically significant evidence to conclude that, and then you just copy and paste H1. The distribution of shower time is not normal. Okay? And then the word the should be not capitalized like I did. Okay, so we have a non-normal distribution. At least we have statistically significant evidence to say that it's not normal. Any questions on this idea? Okay, and the two main things where you want to test for a distribution type One is to test if it's normal. The other, often people test to see if it's uniform. Those are the two most common of the tests. So it's very important to, make sure that you take notes on what we did so that you know how to write the answers down. Because I do take off points if you use the wrong words. Okay. And I noticed a lot of people did that. I graded, today was a big grading day. So I graded a lot today. And last night too. I woke up in the middle of the night and I just graded. And I noticed a lot of you aren't using what's happening in the webinar. So make sure you do. My guess is some of you aren't really listening to it much. But probably not the ones that show up live, but so it is important that you listen. Any questions at all on any of these chi-square tests? All right, so what I want to do now is I want to give you the secret word. And the secret word for the week 9 webinar is qualitative, because as I mentioned from the beginning, is that chi-square tests work great for qualitative data, whereas the rest of the tests that we've had so far in chapters 9 and 10, they don't work at all for qualitative data unless it's yes, no. But here it's qualitative when it's like, what state are you born in? What is your race? What's your favorite color? When, what season were you born in? What car type do you have? So that's all qualitative survey questions. Any questions on the secret word? Qualitative. Make sure you spell it right. Okay, so that was a secret word. So I want to remind you that we have had 3 different kinds of new tests. The chi-squared good as fit test, the chi-squared test for homogeneity, the chi-square test for independence, and the chi-square test for homogeneity. So make sure that you get each of those tests down. It's not that hard, but you have to pay attention. That's all. Okay. And they work especially when, you have a survey question that's not a number and not a yes, no. Any questions at all? Okay, as I promised, today was a little shorter than usual because do you agree this was not as hard as most of these weeks? I try to slow down towards the end, especially, those of you who are like full-time students, that because towards the end you might have a lot of stuff going on. Of course, some of you might be at a semester school and you're not even in class. But if you're at our college, then that's finals happen. It gets really hard. Any questions? Okay, if not, what I'm going to do, as always, I'm going to stop the recording. Thanks for coming.